let's look at this. So we're basically going to be doing some things like the IROG stuff. I'm going to start off with limits. And this is the example question. It wants us to graph this. It's made up of multiple parts, depending on what the x value is. If it's made up of multiple functions, like the first one is just a linear function, looks like this, right? The second one is, how do you graph this? How do you graph y equals 1 or f of x equals 1? What do you think?
You just draw a horizontal line.
Yes. And then the last one is a square root function that's kind of, it's gone to the right by 1 unit. Square root function looks like this. It's going to start at 0, 0, like that. This is y equals to the square root of x. If there's a minus inside of the function itself, you need to do the opposite. So if it's -1, and by the way, inside, it's going to change horizontally. Everything on the inside is dependent upon x. So -1 means you're going to go to the right by 1 unit, and above 2 means you're going to go top 2 units up. So now the question is, how do we graph this? So we know, let's look at the first one. That is a linear function, right?
Mm-hmm.
What is the y-intercept? The y-intercept is -1. What's another point here? We're just trying to graph this, x minus 1. Well, the slope is 1, so you go up 1 unit, you go to the right by 1 unit, like that. And this is -1, and then you just join the dots, and then you'll have your linear graph like that. But this guy only exists when the x value is less than 1, right? You see this?
Mm-hmm.
Less than means open circle or closed circle. It's not inclusive. Inclusive, it's exclusive. So that means there's going to be an open circle there. Okay.
Okay.
The next one, when x is exactly 1, so when x is exactly 1, the y value is 1. Is this inclusive or exclusive?
It's inclusive.
Yeah, so there's going to be a closed circle there. And then finally, when x is greater than 1, our function looks like this. So that function is, it goes to the right by 1 unit. So right now we're at 1, 0, and then goes up by 2 units. So we end up at 1, 2. That's going to be our boundary value, our starting point. So at 1 and 2, so 1 and 2 right there. Is this one exclusive or inclusive? The third one. It's pretty simple to see what it is. If it's equals to like this, then it's inclusive.
It's exclusive.
Yeah, exactly. Exclusive means what? Open circle or closed circle?
Open.
Yep. Yippity doopity. Like that. And then you don't have to be super precise with this. You could if you wanted to, but we don't care about it here. So it's going to look like that. Okay, now if you remember, for a limit to exist, the limit on the left-hand side, 1 minus. 1 minus doesn't mean -1, by the way. 1 minus just means the x value there is 1, right? 1 minus just means slightly to the left of 1. The limit slightly to the left of 1 must be equals to the right-hand limit 1 plus, like this. Okay?
Mm-hmm.
Can you tell me what the y value is for 1 minus? So we're looking at it right here. What's the y value? What is it approaching?
1.
1, right? So this guy is 1. What about 1 plus? So now when you're thinking about 1 plus, you got to look at, so this function doesn't exist for 1.01, right? 1 plus means slightly to this one. You can't use that one. This one also does not exist for 1.01 because it only exists at exactly 1. The first one exists at less than 1. So you have to look at the third function here. So let's look at this one. Slightly to the right of 1, what y value does it approach? the open circle has a y value of 2, right?
Mm-hmm.
So that means this guy approaches 1 plus is just simply going to be a 2. The first one was 0 actually, because the y value here is 0 like that. So are these equal?
No.
No, right? So that means limit does not exist. And that's it. There's one more thing I would like to mention here. The idea of continuity. Continuity just means continuous. It means like, think about when you're graphing anything, right? If you have to lift your finger up, that means it's discontinuous. Like for example, if you want to graph 1 over x, you can do this in one stroke, right? But then 1 over x looks like this. There's no way you get from here to there without lifting your hand. So this is discontinuous. There's a way to find out whether something is continuous or not. Something is continuous if it's left-handed limit. You can call this a minus, I guess. We don't know what it is, but if its left-handed limit is equals to its right-handed limit, that means the limit exists, okay? But at the same time, it also has to be equals to f of a. So now what does all of this junk mean? The idea is pretty simple, actually. Let me give you an easier function to work with so we can make sense of what is continuous. I'm going to keep this graph because I like it. Let's look at a new function. Y equals x squared. You remember what that looks like? Looks like AU, right? Like that. And it goes through the origin. Now let's look at this. That point there is 0, 0, the origin. What is the limit as x goes to 0 minus of f of x? Which means when the value is slightly less than 0, right, or directly to the left of the 0, what's the y value? Look right here. What's the y value right there? What is it?
0.
It's 0, right? What about on the right side of 0?
It's still 0.
It's still 0. What about what's the value? If f of x is x squared, what's f of 0? All you do is you replace this x with what you have in the bracket, right?
It's 0.
It's 0. See, notice all 3 of these guys are the same. That means this function is continuous. What about this one? Is this continuous?
No.
No, it's not, because it doesn't satisfy either of the pact. It doesn't have a limit, first of all. And even if it did have a limit, it's not going to be equals to the y value when the x value is 1. So this one is discontinuous, okay?
Okay.
Discontinuous. I'm going to ask you a 10-point question. Are there any restrictions on f of x? Let's go one by one. Is there any restriction on this? Is there any x value that it cannot be? Think about a straight line, right? X minus 1. Can x be anything?
It can't be more than 1.
Oh yeah, forget about this for now. Just look at this function. Y equals to x minus 1. Does it have any restrictions?
No.
No. Y equals to 1. Does this have any restrictions?
No.
What about the third one? Y equals 2 plus square root of x minus 1. Does this have any restrictions? Yes, it does. Okay, because you cannot take the square root of a negative number. So what that means is, you see this bracket here? Whatever is inside the square root, whatever is inside of the square root must be greater than or equal to 0. Okay? How do you solve this linear inequality? X minus 1 is greater than or equal to 0. What's x? This one you've done. This was your last test.
It's just 1.
Yeah, there we go. So these are polynomials. You can see. The first one's a polynomial because it's x power 1. Is y equals to 1 a polynomial?
No.
Turns out it is, because to be a polynomial, you can just write x to the power 0 there. Okay, so a number is a polynomial. And polynomials are pretty easy to work with, and also to find the IROC of, because you can just use the power rule. And it's always continuous. Polynomials are always continuous. Cool?
Uh-huh.
So basically the limit, I want you to think of it this way. Let's say we have some point A, right? We don't know what that x value is. It does not matter for us. Let's say we have some curve like this. Now, what does a limit mean? The limit means the y value, okay? When does a limit exist, I guess? When the limit from the left side is the exact same thing as a limit from the right side. Only then does a limit exist. And if that value is exactly equals to this value here, then that means it's continuous, okay? That's the idea, and it's pretty simple. I'm gonna ask you a question that's beyond us, but we're gonna ask this anyways. Let's say this is the curve of x squared. How many independent variables do we have?
Two.
No, y is dependent upon x, so only one. X is the independent, right? Because y depends upon x, so there's only one independent variable. And this is how it's gonna be, okay? But eventually, if you're, I don't know, eventually you might run into something like this. Z is equals to xy. How many independent variables do we have now?
There's two.
There is two, right? Now, what if I asked you, what's the limit as xy goes to 0, 0? Last time only x was going to 0 because we had one independent variable. Now we have two different independent variables like this. And actually, let me show you what this looks like, because it's actually pretty interesting. To graph this, Desmos is not going to help us. We need something else, because it's going to be in 3D, okay? This is what it looks like. Pretty cool, right?
Uh-huh.
And you can play around with this actually. Like, what if I just did over x squared? Oh no, x squared doesn't help. Square root of x. No? Okay, it killed off a section of it. What if I times this by a circle? I don't know. I just have, sometimes it's fun to see what shape that you end up with. And yeah, but for us, our shape was just xy, which looks like this. It's pretty funky, right? And the question is, what is the limit when both x and y are 0? Yeah, that's the question here. But now we're gonna run into an issue, because the thing that we just, again, this is just for further knowledge, right? This one is just for curiosity, you know, to understand this super well. But when you're dealing with things in 3 dimensions, like this one is going to be a 3-dimensional surface, the idea of the limit of the left side being equal to the limit of right side and limit existing fails. Now, why does this fail? This guy, we just saw this, right? It looks like, how do I even draw this? Like, this looks like this. On one side, on the other side, it looks like this, looks something like that. Okay. Now you're trying to get here, right? You're trying to get here. Here it was easy, because the only way to get there is through you follow this line this way and you'll get there, or you follow this line there and you'll get there. Yeah. Now when you're talking about a surface, then things fail, because to get here you can either go this way, you can go this way, you can go this way, you can go this way. Look, are you seeing this? There's so many ways to go there. How many ways are there to get to that point? There's an infinite number of ways to get to that point. So this idea here, this fails for limits of a multivariable function like this one, when you have multiple independent variables. To find that, actually, this one is pretty simple, because this one, are there any restrictions on what x and y can be? There is no restrictions. This is still a polynomial. You just plug x as 0, y as 0 is 0. The limit for this one is 0. But things get way more difficult if you have something like this, x over y. Now you can't just plug x and y as 0, because then you would get a 0 over 0, right? So yeah, things are gonna fail when this happens. I don't know, let's just do this. I don't know. I think this is gonna be, I just want you to understand what limits actually means. So x over y. So plug and chug fails here. That's the first thing you would do anytime you're trying to find limit. Plug and chug fails. And there's multiple ways to get to that. There's no two ways like the left hand, right hand, like we did in the previous question. So now what do we do? What you need to do is you need to write one variable in terms of the other. Okay? Write one variable in terms of the other. What I'm gonna assume is that y is x. Like if we had x squared over y, then I would assume y is x squared. Basically, you need to write one variable in terms of the other, okay? So what
Okay.
this means is y is fixed. So we're not worried about y. So what now this becomes is that the y just disappears. We're not worried about y because it's fixed. You get a limit as x approaches 0 of x over x, yeah?
Mm-hmm.
See, this cancels out. Then you have a limit as x approaches 0 of 1. There's no variable here. You can ignore this. The limit is 1. So it does exist. So that's how you would go about doing this. With this one, honestly, this can get difficult really, really quickly. And in order to kind of see it, you need to visualize it, which is, we're not there yet. I don't think we'll get to this anytime soon, if ever, because that's like, unless you go into like a math field or a physics field, you won't have to do the multivariable thing that we're talking about. But this one though, this one everyone does it in high school. What's the high school grades like? From 9 to 12, is it?
Here
In,
it's 10 to 12,
so what is 10 called? 10 is called freshman?
I guess. Cause you stop in elementary like at grade 6, and then you have to go to junior high from 7 to 9, and then
Okay,
it's high school.
interesting.
It's kind of weird.
Let's keep going here. Notice, look at the pattern in question 4. Again, don't worry about the multiple independent variables. We will never see that, but we're more interested in just y and x. What's the pattern here? What's similar about all of these functions? They all have one similarity. Do they have any restrictions? Look at all of them. Most of them are polynomials. It's polynomial. The only one that's not a polynomial is f. But even f, that's an exponential function, that is still continuous. 2 to the power of x looks like this, right?
Mm-hmm.
So if a function is continuous, and even if you don't know it is, when you're trying to find a limit, you should always plug it first. Okay, just straight up plug it in. And if it's continuous, you'll get the limit straight away. You don't even have to do any maths. Look at this first one. I'm just going to plug x as -5. -5 is the answer. For b, this is what I like to call plug and chug. Basically plug it in, and it's going to work out sometimes. Most of the times it does not. So the next one is also, it's going to work out for all of these because everything here is continuous. 4 minus 3 times 4. So -8. What do you think the answer to E is? The limit of 4 as x approaches 1. Basically what that means is you imagine a graph of y equals to 4. Looks like this, right?
Mm-hmm.
What's the y value when the x value is 1? What's the y value here?
It's 4.
Yeah, exactly. So this x being anything doesn't impact. If it's a constant like 4, doesn't matter. It's still going to be 4. If x was pi, it'll be 4. If x was -infinity, it'll still be 4 because it doesn't change. The y values don't change. Yeah?
Mm-hmm.
What's the answer to f? Just plug it in. Plug x as 3 straight up because this is a continuous function. Even if you didn't know it was continuous, just first plug it in and see if it gives you a number. Yes, it does. But plugging it in doesn't always work. For example, if we had y equals 2 to the x over x, the limit as x approaches 0, right? Look at this. This is going to fail because now you have 2 to the power of 0 over 0. Anything to the power of 0 is 1 over 0. See, now you've hit a conundrum. 1 over 0. So the limit more than likely, it does not exist. Because 1 over 0 means mathematically what that means is like there's an asymptote. There's like an invisible wall. Usually that's what dividing by 0 means, okay?
Okay.
So, but for all of these guys though, pretty simple. You straight up plug them in. Let's look at the next one. All right, this one. If x is not 4, the y value is 1. If x is exactly 4, then the y value is -1. Is this inclusive or exclusive at this point?
It's inclusive.
Yeah, so when x is exactly 4, you have a closed circle, -1. But then when x is not 4, you have y equals to 1. Now you know what the graph of y equals to 1 looks like. It looks like a straight line through the y value of 1, right? Goes through, except it doesn't exist when the x value is 4. But then it's going to continue again here. Okay, there you go. That's going to be the graph. Notice there's a jump. From here you go to here, and then from there you go back up here. This means the function is not continuous. So plugging it in may not work because it's not continuous. So what you do here is that you find the left-handed limit and the right-handed limit. Look at the left side of 4. What's the y value that it's approaching? Left side just means 3.99, like right there. What's the y value?
It's 1.
It's 1. What about on the right side? What's the y value?
It's also 1.
It's also 1. So what's the limit? What's the answer to this question? Well, it's going to be 1, right? Because the left side limit is equals to the right side limit, and it's 1, and you're done. Okay? But what is f of 1, though? Oh, sorry, not f of 1, f of 4. What's the y value when the x value is 4?
It's not there.
It is there. It's -1, right? When the x value is 4, the y value, when the x value is exactly 4, the y value is exactly -1. Now, the limit exists. We know this, okay? Because this and this, the left side, like here, these were equal, the limit exists. But the fact that the limit is not equals to the y value when x is exactly 1, this means it's not continuous. Okay? Notice the distinction. All right. We may have done this, but let's just kind of hammer this point home. And it's actually pretty simple. The fact that they've already given you a graph makes it even easier. This is also a piecewise function. First question to you, is this continuous? Is this graph continuous?
No.
No, it's not, because it jumps, right? It's just boing, boing, it jumps. Jumping is always discontinuous. Let's look at this one by one. The limit -2 plus means find -2 first, right here, when the x value is -2. Plus means we're looking to the right side of -2. What's the y value there? What is it approaching?
0.
0. What about -2 minus? So we look at the left side of -2. What's the y value that it's approaching?
0.
0. Now we're looking at 2 plus. So let's find the x value of 2, which is here. Now we're looking at the right side of 2. What's the y value that it's approaching here?
-1.
Yeah. What's f of 2? What's the, now this has, the last question has nothing to do with limits, D. It's asking when the x value is 2, what's the y value? When the x value is 2, look at this. This point is inclusive, right? So when the x value is 2, the y value is also 2, like that. Does the limit exist at -2? Compare the left hand and the right hand sides. At -2, does the limit exist?
No.
Yes, it does, because the left side gave us 0, the right side also gave us 0. So -2, the limit, this question is not asking us, but -2, the limit is 0. Because the right side is 0, the left side is also 0.
So
What
they
ab-
just have to be equal?
They just have to be equal, yeah. What about at 2? Does the limit exist? When the x value is 2.
Yes.
So when the x value is 2, from the right side, we get -1, yeah?
Mm-hmm.
What do we get from the left side? We get a
Oh,
2.
you just get 2?
Yeah, so it's not equal. So limit does not exist at 2, okay?
Mm-hmm.
That's the idea. You just have to check to the right of, to the left of. Here, 7a, what's the limit when the x value is 2? What's the limit right here? What is it approaching from the right side? The y value, yeah? Here's 2. From the right side, it's 2. What about from the left side? What's the y value?
It's also 2?
It's also 2. And the fact that when x is exactly 2, y is exactly 2, right? So
Mm-hmm.
these two pieces of information tells us that the limit is 2, okay? And then this extra piece of information, when the x value is 2, exactly 2, the y value is exactly 2, means it's also continuous. Whatever we're working on, it's continuous at this point. And x equals to 2, the function is continuous. Let's look at b. What's the limit on the right side?
2?
No, it's not. Try
1?
1, right? The limit on the right side. What about on the left side?
Also 1?
Does it exist?
Yes.
Yeah, it's 1. Trick question, is this continuous?
No.
No, it is not, because when x is exactly 2, y is 3, but the limit is 1 when x is 2, right? When x approaches 2. So b is not continuous. And we know just by looking at the graph it's not continuous, because from here we'd go all the way up. If we jump here, we kind of teleport, open a portal, and then we're going to open a portal right back down. This is called a hole in the graph. Like when you have something over a 0, you get an asymptote, okay? Like an invisible wall. A hole in the graph is when you have a 0 over a 0. For example, this graph, x minus 2 over x minus 2, when x is 2, there's going to be a hole in the graph, because when x is 2, you get a 0 over a 0. The graph of which looks like this. Okay, so a hole in the graph usually means there's a 0 over a 0 situation happening. Let's look at C. Find the limit when the x value is 3. So let's look at it from the left side. What's the y value that it's approaching from the left side?
-1?
What about from the right side?
1?
Yeah, so what's the limit? Does it exist?
No.
No, it does not exist. Is it continuous?
It's not.
Nobody, right? No, it is not continuous. So that's it for that question. And you're gonna see soon that the plug and chug is gonna start failing. It only works if the function is continuous at that point anyways. So step 1, it doesn't matter what the question is, always try and plug it in. And when you plug it in, you get something weird, then you start trying to do some things. This one, you can just plug it in. The answer is 8. Just plug x as -1. And we know this is going to work out because this is just a negative quadratic function, which is continuous everywhere. B, let's plug x as 0. So you get 0 plus 20 on the top, and on the bottom you get this. This is 4. Right? Like this. So what this means is that when x is 0, this function is continuous. Same thing here, square root of 5. When x is 5, this function is indeed continuous because square root of 4, which is 2. That guy is just looks like this, goes to the right and then goes up like that. And that's the graph of this. When x is 5, look at it, it's continuous, right? There's no jump here.
Mhm.
And usually when you plug it in, it works out. That means the function is continuous at that point. These are also all mostly plug and chug. All of them are plug and chug actually. Except this one. Yeah, let's do this. Everything else, you can just plug the 3 in. Yeah, everything else is good. This one is not good. What happens when we plug a 3 in?
You get 1/0, which you
Yeah,
can't do.
no, you can't do that. That means there's an asymptote there. That means the function is discontinuous there. But that doesn't mean it doesn't have a limit. It just means it's discontinuous, right? Like we saw in the previous question, if you had something like this, the limit does exist. It's gonna be whatever the y value here is, but it's not continuous. Same idea here. It's not continuous, but we don't know if the limit doesn't exist. So what do we do here? What you need to do is, ideally, if you know what the graph looks like, that would be perfect. This is what the graph looks like. 1/x looks like this. Okay.
Mhm.
There's an asymptote at 0 on the y-axis. This -3, always in any functions, if something's happening to the x, that means it's either going to move left or right. So x -3 means it's going to move 3 units to the right. So this, you see the asymptote was on the y-axis. Now the asymptote is going to be at exactly 3. Okay, so your graph is going to look like this. Like that. Question to you. When limit x is going 3 minus, so to the left side of 3, where's the y value going? Where's this value going? It's going all the way down, right? It'll never cross this barrier. In fact, it's going to negative infinity. What about on the right side of 3? So we're looking at this because that's like 3.01, right? It's never going to cross that wall. Where is that going?
Positive infinity.
Yeah, so does the limit exist? Compare these two.
No.
No, it does not, because the left-hand side is different from the right-hand side. So the limit at x equals to 3 does not exist. Cool?
Mhm.
I'm trying to find some interesting ones. Okay, we can quickly do this. I know it looks annoying, but it is what it is. So x plus 2 means you have a y-intercept of 2, right? So 1, 2, and then for every 1 unit you go up, you go 1 unit to the right, like that. And this function only exists when the x value is -1 or less. So I'm going to erase this thing because it does not exist when the x value is greater than -1. Open circle or close circle for this guy?
Open.
Yeah, so like that. There's an open circle there. The next guy, -x plus 2, same idea. It's going to start here, but instead of going 1 unit up and 1 unit across, the slope is -1. So it's going to go 1 unit down and 1 unit across there. And that guy exists from -1 onwards, like that. Is that an open circle or a closed circle?
Closed.
Yes. Okay. So the y value here is 2. The y value here is -1. This is -1. So tell me, they want the limit when x is going to -1. What's the limit when x goes to -1 from the left? So we're looking here, yeah? When x approaches -1, what's the y value?
1.
1. What about the other side? When x approaches -1 from the right, what's the y value? So we're looking up here. -1 from the right means just directly to the right of -1.
It's 3.
Yeah, it should have been 2. Let's say it's 2. Cool.
Mhm. So there's no limit.
Nope, there is no limit, and it's also not continuous. Alrighty?
Uh-huh.
And you're done. 1 and done. Easy? Easy enough, right? When they give you a graph, it's super simple. And even if they don't give you a graph, how hard is it to graph x plus 2 twice? Let's try this one. The first one is y equals to 4x, correct? Correct, Amundo? How do you graph that? What's the y-intercept?
0.
0, right? So you're gonna start at 0, and then you're gonna go how many units up?
4.
4 units up, 1 unit across. But this only exists from negative, from a half, okay? So what you could do is this is what I like to do, but you obviously don't have to do this. I'm gonna connect those two, and then I'm gonna erase because this guy only exists when the x value is a half. So right there. Right there. And that point is 2. So there you go, that's the first guy. Now the second guy is a little bit weirder to graph. 1 over x looks like this. So I guess on this side, we don't really have any issues. But on the other side, we do. When x is 1 over 2, what does 1 over x give us? So let's say y is 1 over x. When x is 1 over 2, what's the y value?
It's 2.
Yeah, it's 2. And I'm gonna bring it all the way from here, right? Like that. And boom, it's gonna end right there. But this guy is not inclusive, right? But look at what's happened here. We had a closed circle from the first guy, right?
Mm-hmm.
We have a second guy coming in there with an open circle, but then this plus this at the same point, the circles are gonna overlap. It's gonna basically become filled. What this means is at 1 over 2, the function is continuous. Even though this one had an open circle, but at the same y value, the other guy has a closed circle. So it's going to fill up this gap here. So at 1 over 2, the function is continuous. Okay?
Okay.
So tell me, what's the limit when x is 1 over 2?
Is it just 2?
Yeah, it is. It is. And I didn't graph this right. I should have, yeah, so this green bit doesn't exist actually. Like, what it should have been was it should have been like this. It should have gone up like that, yeah. But yeah, it's 2. It's 2. Because right there, same idea, right? This one has a closed
Mm-hmm.
circle here, but this one has an open circle, yeah, because it's greater than the limit is 2. Is this continuous at 2?
Yes.
Yeah, it is, because there's no open circles or any discontinuities there. I don't want to do that. So those are easy ones, right? Like, look at this one. Is this function continuous everywhere? It is continuous everywhere, right? How do you know? What's the function that we're dealing with? It's a quadratic, right? X squared. X squared is continuous everywhere. So you see, you can straight up, and again, even if you don't know it's continuous, you straight up plug the 2 in there. So this is just a simple plug and chug on the calculator. Gives you a 19. But this one, we may run into some issues. Is this continuous everywhere? Probably not. Because this is a rational function. Like, if the denominator were to be a 0, then we would be screwed, right? We don't know where it's a 0, though. So it doesn't change anything. What we're gonna do, step 1, we're gonna plug x as -1. So you get 1 plus 5 plus 2 on the top. On the bottom, we get -2 minus 3 plus 1. That doesn't change anything, actually. You just get 8 over -4. The answer is -2. Cool. This is just a plug and chug, yeah. So we don't know if this function is continuous everywhere, but we know for a fact that it's continuous at -1 because we didn't get any asymptotes or holes or anything weird. So you can plug that in. What about this one? Is this continuous at 5? Well, let's find out. So we have 5 squared over 5 minus 1. So we have 25 over 4 square root. The answer is 5 over 2. Take the square root of the numerator, take the square root of the denominator. Or even plus minus. But I don't think it can have multiple limits. It's going to be strictly plus. Like that. Okay?
Mhm.
So most of them are just plug and chug. Now here is where we're going to run into an issue where plug and chug is going to fail. Because you can see, just look at the denominator. If x is 3, then we get something weird. We would for sure get a denominator of a 0, right?
Mhm.
So what's the idea here? So when the plug and chug fails, which it does here, there's only one thing you can do, and it's to simplify. Try to cancel things out, to factor things. Can we factor the numerator?
No.
We can, I guess, factor the numerator because it is a quadratic trinomial, right?
So you can use man.
Niels, man, what are the numbers out straight up? What does it factor out to? It's going to multiply to -3. It's going to add to -2. What are the numbers, I guess?
-3 and 1.
Yeah, so it's straight up going to be x minus 3, x plus 1, okay?
Uh-huh.
So what this means is that I guess the limit as x approaches 3 becomes this. And then notice we have an x minus 3 on the top, x minus 3 on the bottom, like that. They cancel out, go to Narnia. What are we left with? You're just left with the limit as x approaches 3 of x plus 1, like that. Now you plug it in. It becomes 4 plus 1, 5, and you're done. So it does exist at x equals 3. Cool?
Mhm.
Is it continuous at x equals 3?
Yes.
No, it's not, because what happens? Look at what happens when x is 3. You get a 0 in the denominator, right? In
Oh.
fact,
Mhm.
if you plug x as 3 into the factored form, you'll see you get 3 minus 3 over 3 minus 3, you'll get 0 over 0 times x plus 1. It is not continuous. You have a hole when x is 3. Graphically, this is what it will look like. So you're only left with x plus 1, so this is what you're going to be graphing. The y-intercept is 1, the slope is 1. So you get this, but then when you go to the x value of 3, you're going to have a hole in the graph like that. So even this is not continuous, okay?
Uh-huh.
Because there's a hole in the graph. Same idea here, but this one's going to require you to do the first thing that we did when we started doing this thing. If you plug x as 0, this is going to fail because you're going to get a 0 in the denominator. So that is no good, right? How can we simplify this expression? I'm going to get rid of the square root on the top. What do I multiply it with? You remember that?
With square root of x minus 1.
No, that's not the conjugate here. Right idea, wrong execution. It is x plus 1 plus 1. If it was just x plus 1, then it would be x minus 1. But here, it'll be x plus 1 plus 1. Because the goal is to use the difference of squares. So you need a and you need b, but the signs between them has to be different. Okay? So it's not,
Okay.
that's going to be the conjugate in this case. And whatever you multiply by top, you need to multiply it by the bottom as well. Like that. Because these two cancel out. It's just, you're just multiplying by a 1 already. So on the bottom, nothing changes. Well, something changes, but you don't have to worry about the bottom. So I'm just gonna write this as x times x plus 1 plus 1. Use difference of squares. What do we get on the top? See, we have a minus b times a plus b. We get a squared minus b squared. If a is square root of x plus 1, what is a squared? Remember with the squared and square roots, they just cancel each other out, okay?
So you just get x plus 1.
Yeah, so you just get x plus 1. So you get a squared, which is x plus 1, minus b squared. Well, b is 1, 1 squared is 1, so like that.
Mhm.
And 1 and 1 cancel out, so you're just left with x over all of that thing. And now even the x cancels out. So you're left with limit as x approaches 0 of 1 over x plus 1 plus 1, like that. And once something cancels out, usually it's going to work out. So let's plug 0 in there as x. Like we did when we cancel out the h's, we are allowed to plug h as 0, same idea here. We canceled out the x's, now you plug x as 0. So you get 0 plus 1 plus 1. So the answer is 1 over 1 plus 1. 1 over 2 is the limit. Cool.
Uh-huh.
Is this continuous?
It's not.
No, it's not, because we already knew that you would get a 0 in the denominator. This is a whole. When we, how do I know it's a whole? Because when you plug x as 0, you would get 0 plus 1, square root of 1 minus 1 over 0, square root of 1 minus 1, that's still a 0. So you get a 0 over a 0 situation, so it's a whole. Okay? If you had
Mhm.
got a 1 over 0, then that would mean it is it's something else. That's an asymptote, a vertical asymptote, like an invisible wall. This one you can see straight up, it's not continuous because you get a 0 in the denominator, right?
Uh-huh.
What do we do in this case? So limit as x approaches 0, yeah, of
Mhm.
x plus 8. And again, what does to the power of 1 over 3 mean?
Cube root of 8.
Yeah, cube root of x plus 8, the entire thing, like that. Okay, if you plug x as 0,
Uh-huh.
it's gonna fail. So now the question is, what do we do? What is, I guess, we need to somehow get rid of the cube root, right?
Mhm.
So what do we multiply it by? I guess it's the question.
Itself.
Would that work? No, let's see. You have cube root of x plus 8 plus 2,
Plus.
and then you have the same thing, but then you have cube root of x plus 8 times cube root of x plus 8. Do the cubes cancel out? No, they don't, right? It only cancels out when it's a squared. Basically, what we have right now is we have x plus 8 to the power of 2 over 3. Okay?
Mhm.
That is not going to help us. I don't think so. You understand why, though? Because square root of x plus 8 squared would kill off the roots, right? But when you have a
Uh-huh.
cube root of x plus 8, and if you multiply it with itself, you get a 2. That
So
and
they
that,
don't.
no, they don't cancel out. Yeah, so there's only one way to do this, and this is a little bit advanced. It's called a substitution method. Basically, you cannot find a conjugate of this to multiply it with. What you do is you take this entire term actually, because you don't want anything like that. So you let u be, they did it somewhere here. X plus 8, u just means you're introducing a new variable, right? Like that. Then you cube both sides, you get u cubed is x plus 8. Okay.
Uh-huh.
That means even x is gonna be u cubed minus 8. So you replace this thing with u, right? Then replace this with u cubed minus 8. And then from there, you got to use a difference of cubes. This one's pretty advanced. Don't worry too much about it. These ones we can do though. And we'll do those as well once I think you can do them by your own, we'll do those. Let's do this. So 3 minus doesn't change anything. What you should do is you should straight up plug it in as 3, okay? Not minus 3, but as 3, and see if it works out. Yes, it does. Okay.
Mm-hmm.
Let's look at the restrictions of this function. How do you go about finding what x can be or can't be? Look at the inside of the square root. What's the restriction on the inside of a square root? The inside of a square root always must be what? Positive, right? Or 0 or positive. It can never be negative. Has to be a non-zero number. Do you agree?
Uh-huh.
So that means is 9 minus x squared must be strictly greater than 0, correct?
Yes.
So 9 must be strictly greater than x squared. So what this means is, if you remember the graph of the quadratic, this means that x is strictly between -3, okay, and +3. Look at this graph. This is -x squared plus 9. Looks like this, okay? There's a 9
Mm-hmm.
there, but it has to be strictly greater than or equal to 0. It's 0, it's equal to 0 at -3 and +3, and it has to be strictly positive. So basically we're erasing this part of the graph. So there you go. That's the restriction. X has to be strictly less than 3, but greater than -3. Okay.
Okay.
Which is going to help us find part B. Why does the limit not exist when x approaches 3 plus? What's the upper limit of x?
3.
3, right? 3 plus, there's nothing. This function doesn't
Mm-hmm.
exist at 3 plus. That's why this cannot be determined. So that means the limit as x approaches 3 plus of f of x, whatever this is, it does not exist because the function does not exist there. To 3 minus, we know 3 minus was 0, right? So what's the limit at 3? At 3 plus, it doesn't exist. At 3 minus, the limit is 0. What is the limit at 3?
It doesn't exist.
Yeah, it doesn't exist because left-hand side is not equal to the right-hand side, and you were done. Okay?
Mm-hmm.
Left-hand side does not equal right-hand side, so it is nada. Most of these are plug-in chugs. And that's what you're always going to do. Even if you don't know what it looks like, this is going to be, everything here is going to work out. Everything here is going to work out, I think, except some of these don't work out. Let's try one more. If you plug 2 in there, you get 4 minus 4, you get a 0 on the top, but you also get a 0 on the bottom. So this is a hole question. There's going to be a hole on the graph somewhere. Any ideas on how to factor the numerator? The numerator is a difference of squares, if it helps. It's in the form of a squared minus b squared. What is it gonna be? A squared minus b squared. It's a minus b times a plus b. A minus b times a plus b. So this is a squared, that's b squared. That means a is 2, b is x, right? You understand this?
Mm-hmm.
A squared minus b squared. So it's going to become 2 minus x, 2 plus x over 2 minus x. This cancels out. And then you plug 2 in there. So 2 plus 2, the answer is 4. The limit is 4. It does exist. It's just not continuous. There's a hole in there. And that's it. Okay?
Okay.
All right. We're done for today.
All right. Thank you.
Bye.